Hello and welcome to yet another video of Cornerstones of Math. Today I will discuss about nested radicals. That is, expressions containing a radical sign inside a radical sign. I will talk about denesting, the method of converting such nested radicals into expressions that do not have any nested radicals. Not every nested radical can be denested, and I will only discuss about the simplest case of nested radicals in square root of a plus square root of b form. Now, if you already saw the thumbnail, you'd know that I will present you two methods or formulas of denesting. I will discuss each formula in more detail, so let us start with the first formula. The first formula is applicable to the nested radicals in the form of square root of x plus y plus 2 times square root of xy. That is, this part is the sum of two numbers x and y, and this part is the product of two numbers x and y. In this case, we can write x as square root of x squared and y as square root of y squared. Then we have 2 times square root of x times square root of y. So by this formula, we can write the inner part as square root of x plus square root of y squared. So we have square root of x plus square root of y. Now let's take a look at some examples applying this first formula. For the first one, we must first convert this inner radical part so that we have this 2 at the front, and you can easily find that square root of 60 is 2 times square root of 15. Now we have to guess, what are two numbers x and y whose sum is 8 and the product is 15? This is pretty easy guess since 8 is 5 plus 3 and 15 is 5 times 3. This means that the entire inner part is square root of 5 plus square root of 3 squared, which gives square root of 5 plus square root of 3. Now let's take a look at the second example. In this case, we cannot make 2 here by taking it out from the inner radical. So what we do here is writing the inner part as a fraction with 2 at the denominator and write 8 plus 2 square root of 7 in the numerator. This can be written as square root of 8 plus 2 square root of 7 divided by square root of 2. And now we apply the formula. Notice that 8 is 7 plus 1, and 7 is 7 times 1. So we have square root of 7 plus square root of 1 divided by square root of 2. Rationalizing the denominator by multiplying square root of 2 at the numerator and the denominator, we have square root of 14 plus square root of 2 divided by 2. So this is how you apply the first formula. And now let's take a look at second formula. This formula can be applied to the original square root of a plus square root of b form without having to take 2 to the front here. First, we have this expression. This formula is always true as long as the inside of each radical sign remains non-negative. But here, both terms on the right-hand side are still nested radicals, right? Well, as I just said, this is a general formula, but in special cases where a squared minus b is a perfect square, k squared, then this formula becomes a denesting formula, which is square root of a plus k divided by 2 plus square root of a minus k divided by 2, where k is a square root of a squared minus b. Alright, so to recap, one special case where this can be denested is when a squared minus b is a perfect square, and in that case, we can simply plug in numbers in places for a and b to obtain a denested form. So for the next step, let us prove this identity. For a start, let's write this as square root of u plus square root of v. And if we manage to find the expressions for u and v, then we have the formula. Now, let us square both sides. Then we obtain a plus square root of b equals u plus v plus 2 times square root of uv, which equals u plus v plus square root of 4uv. Here, one way this can be true is that u plus v equals a and uv equals b over 4. So the question is, are there u and v satisfying these two conditions? Well, yes, there are. And we will use the property that the quadratic equation t squared minus u plus vt plus uv equals 0 has u and v as its roots, because this equation is equivalent to t minus u times t minus v equals 0. So using our values for u plus v and uv, we have the quadratic equation t squared minus at plus b over 4 equals 0. Using the quadratic formula, we have roots a plus minus square root of a squared minus 4 times 1 times b over 4 divided by 2, which equals a plus minus square root of a squared minus b over 2. So if we simply let u as a plus square root of a squared minus b over 2 and v as a minus square root of a squared minus b over 2, then you can notice that we obtain the formula that we wanted to prove, hence the proof is complete. So now that we've proved the formula, let us tackle these examples again, now using the second formula. For the first example, notice that if we calculate the a squared minus b part, we obtain 8 squared minus 6t, which is 4, which is 2 squared. So a squared minus b is a perfect square, meaning that this nested radical can be denested. And straight from the formula, we have square root of first 8 plus 2 over 2, then 8 minus 2 over 2, so we have square root of 5 plus square root of 3. And for the second one, we have a squared minus b equals 4 squared minus 7, so 9, which is 3 squared. So here, a squared minus b is also a perfect square. So we have square root of 4 plus 3 over 2 plus square root of 4 minus 3 over 2, which gives square root of 7 over 2 plus square root of 1 over 2. Here, we can write the first term as square root of 14 over 2 and the second one as square root of 2 over 2. So we have square root of 14 plus square root of 2 divided by 2. Finally, I would like to quickly mention that these two formulas we've studied so far are equivalent, meaning that they are basically the same thing expressed in a slightly different manner, and that one formula can be readily converted to the other one. Now, I don't want to explain it in detail here because it is kinda obvious and this video is already long enough, but if you're curious, I will leave a simple exercise right here where you can pause the video and do it by yourself. And that was all for today's video. If you want to take a look at other nested radical problems, please go check these videos as well. And as always, I will see you in another video.